In the previous video, you got introduced to the idea of an ionic compound. That was a metal and a non-metal, or possibly something that contained a polyatomic ion that were held together by the transfer of electrons. The transfer of electrons ultimately meant that there were charges on different parts of the compound. So something that lost electrons ended up with a positive charge. Something then gained those electrons in return and gained a negative charge. Those two stick together because opposite charges attract. Now, we're going to look at a slightly different type of compound today, and that's what we call a covalent compound. Covalent compounds are made of two nonmetals or two or more nonmetals that are held together by the sharing of electrons. The sharing of electrons means there is no charges at all inside of any of these molecules. So a covalent compound is not held together by charges, but held together by the sharing of electrons. So let's take a little bit more in-depth look into a covalent compound. So like I had mentioned, a covalent compound is a compound that's held together by the sharing of electrons. And we can actually see this in the very name. The prefix that's used in the name covalent is co. And co means to share or to have together, like to cooperate, right? You operate together or you share the workload. If you have a covalent, what that means is valent or valence is together and shared. And in chemistry, valence or valent refers to the outside orbital. So the outside orbital is actually going to share electrons to hold a compound together. And like I had mentioned, this is going to lead to something that has no charges. So we're going to do an example that you're actually probably pretty familiar with, and that is water, H2O. Now you may be thinking, okay, H2O, that's not a metal and a nonmetal. Well, if you look at your periodic table, remember the nonmetals are on the right-hand side of the staircase, but hydrogen is also a nonmetal. So if you kind of imagine this staircase actually runs all the way across the top and divides right there as well, that's probably a more accurate view. So hydrogen, and then from boron over, silicon over, arsenic over, tellurium over, and astatine over, those are all the non-metals. When two or more of those combine together, that's what creates our ionic compounds. Now, so water is made of hydrogen and oxygen. It's made of a metal, two non-metals, and that means it's going to be covalent. Now, to understand how it's held together, let's first of all take a look at oxygen. So remember, oxygen is going to have 8 protons based on the periodic table, 8 neutrons, and based on the periodic table and the number of protons, it also has 8 electrons. So in the nucleus, we have our 8 protons, our 8 neutrons. Then we are going to have our first orbital. And our first orbital has 1, 2 electrons. That means I'm going to draw my second orbital. Now, normally I would start up here, but just because of space, actually, you know what? Let's just slide this down. We'll be fine. We'll do this the same way. So we're going to start up here, go 1, 2, 3, 4, 5, and 6. Now, with the other 2, that gives me 8 electrons in total. I want you to notice that I started at the top and worked my way around, putting 1 electron on each side before I made pairs. You see, the reason I do that is because electrons like to be paired up. And so in an atom of oxygen, these 2 electrons aren't very happy. Remember, the outside orbital wants to be full. Atoms want to have a full valence shell, and these 2 unpaired electrons are really kind of messing with that. Now, they also cannot just like combine together to pair up. It doesn't really work that way. Instead, what they do to fill the void of those 2 electrons is they're going to combine with an atom of hydrogen. hydrogen has 1 proton, no neutrons, and 1 electron. So my atom of hydrogen is going to have a single proton in the center, and then it's going to have its outside orbital. Ooh, that was a little wonky there. Let's fix that. And it's going to have 1 electron in it. Now, what's going to happen to make this a covalent compound is that 1 electron is actually going to share an orbital with the hydrogen. So we end up getting our electrons being shared right here. And actually, let's just slide our nucleus over a little bit too. So we'll have our proton there, our outside orbital, and basically this part right here ends up sharing 2 electrons. 1 came from the oxygen, 1 came from the hydrogen. So now they're held together because these 2 electrons are kind of stuck both with the hydrogen and with the oxygen. By doing this, they both have a full outside orbital. Hydrogen has 2 electrons in its first shell. And oxygen, well, it's not quite full yet, but we can fix that because what's going to happen down here is we're going to get another hydrogen atom, so single proton in the nucleus, and then we're going to share that outside orbital, and it's going to have 2 electrons. 1 from the hydrogen, 1 from the oxygen. And now this hydrogen is stuck to this oxygen because the hydrogen has a full outside orbital due to that sharing effect. And the oxygen now has a full outside orbital, making it happy as well. Now, you see by doing this, it's actually made a structure that is what water looks like. It has 2 hydrogens stuck onto 1 oxygen. And this is really what's happening in all covalent compounds. Now, some compounds and certain atoms can share electrons in multiple ways. Something that would be a good example is something like carbon. You see, if we think about carbon and what it's able to do, it can form lots and lots of different compounds that take on different shapes and different structures, and therefore have different properties and work differently. A really good example would be there is carbon monoxide. Carbon monoxide is just CO, 1 carbon, 1 oxygen. But there's also carbon dioxide, 1 carbon, 2 oxygens. There's lots of ways that atoms can share electrons, and so you end up with these different types of molecules that have totally different properties. Now, when it comes to the properties of a covalent compound, that kind of depends. You see, most covalent compounds are not held together by forces as strong as an ionic compound. And what that means is most covalent compounds tend to be gases at room temperature. Think of carbon dioxide, carbon monoxide. There are some, however, that are liquids, and that's because there is a special property in certain types of molecules called polarity. So I want you to think back to H2O. By the time I finished drawing it, it essentially looked like this. Now I'm replacing all of the circles and everything just with the symbols, and I'm showing the connections, the bonds, using little sticks here. Now, what ends up happening in a structure like this is it actually gets a little bit more positive on one side and a little bit more negative on the other. This creates what we call a polar molecule. A polar molecule is one that has slight charges on opposite sides. Many molecules that are very polar tend to be called hydrophilic. Hydrophilic, hydro means water, philic means love. It basically means that they love water. It means that they will mix with water. So think about something like vinegar. Vinegar is basically a type of acid that's dissolved in water. It's called acetic acid. Now, it's able to do that because acetic acid is actually a polar compound, a hydrophilic substance. Because it also has little charges, the charges in the water and the charges in the acid can mix together and they can mingle with each other. On the other hand, there are types of molecules that are called nonpolar. A really good example of something that's nonpolar is carbon dioxide. You see carbon dioxide. Now, I'm going to draw it like this. You don't really need to know what these double lines are, but this is kind of what it looks like. It's the same on both sides of this molecule. And so it means there is no positive or negative on opposite sides. It's actually the same all the way around. This is what we would call a non-polar molecule. It has no charges on any side. We often would call this hydrophobic. And that means fear of water. In other words, it does not mix with water. So a really good example of a non-polar compound would be oil. You see, oils tend to be made out of certain things that we call fatty acids, and they're non-polar. They just don't mix with things that are polar. They don't have charges. They don't mix with things that do have charges. They're just not compatible with each other. And so things that are non-polar, if you try to mix them with something that is polar, they will actually separate from each other. If you ever make your own salad dressing at home, which you should, don't buy like salad dressing from the store, just make your own. It's the easiest thing in the world. What you do is you take some vinegar, you take a little bit of salt and sugar, you mix those together. Those all are polar and have charges and they can dissolve together. Oil is the next ingredient, and oil is non-polar. So you can't actually get the two to mix together, and if you let it sit for long enough, even if you shake it and stir it really, really well, they will separate and they will become different parts of the solution. Non-polar things have no charges of any kind. Polar molecules have very slight charges. Now, you may be wondering, he mentioned at the beginning that covalent substances don't have charges. It's important to keep in mind this is actually just because it's a little bit negative. Not like fully negative, just slightly. And we actually have a symbol for that. And it looks like this. And it means partially positive, partially negative. But the hydrogen itself never lost or gained any electrons, so it's not positive or negative. The oxygen never lost or gained any electrons. It's not fully positive or negative. They are sharing electrons in this bond, and that is why they are covalent. Things that do have slight charges that are polar tend to be held a little bit more tightly, but not as tightly as something that's ionic. That's why water, which is polar, is a liquid at room temperature, and it boils at a somewhat higher temperature of 100 degrees Celsius because the energy to overcome those slight attractions is a little bit higher. Something like, just say, carbon dioxide, it wants to be a gas at room temperature because it has no charges. Nothing's really like holding it together. It doesn't really want to do that. The only exception to this is if you have really long non-polar compounds like oils. You see, really long molecules, they tend to get kind of tangled together, and that can actually allow them to be a little bit more liquid at room temperature. But this is the whole idea behind a covalent compound. They share their outermost orbital with other atoms, and that is what holds different atoms together. Depending on whether they are polar or non-polar will determine their properties, but overall their properties tend to be either liquids or gases at room temperature, and they tend to have lower melting points and boiling points. So hopefully this helps you understand covalent compounds a little bit better. And moving on next, we're going to be taking a look at metals and alloys. So thanks for watching, and I'll see you next time.